What? It was in the bathroom. So anyway, just to recap, because I forgot to turn the video on, this is what 57.9 billion looks like. This is what 5,900 billion looks like. Orders of magnitude is the number of factors of 10, larger or smaller a number is than another number. So when you write these numbers out in scientific notation, you see that this is 10 to the 10, this is 10 to the 12. There's a difference of 2 orders of magnitude, in other words, 2 factors of 10. So that's your answer, that Pluto is 2 orders of magnitude further from the sun than Mercury is. Okay? So just as some other examples here, a kilometer is 3 orders of magnitude longer than a meter, right? Because there's 1,000 meters in every 1 kilometer, right? 1,000 meters in every 1 kilometer. Okay, and if you look at this number through the lens, so that's 1,000, right? If you look at that through the lens of powers of 10, that's 10 to the 3rd power. All right. A dollar then is how many orders of magnitude greater than a penny? 2. Which means it's 100 times greater than a penny, right? Okay, so New York City with 8 million persons is how many orders of magnitude bigger than Earmuff Junction with a population of 8? 6 is right. Okay, cool. So that's orders of magnitude. Any questions on that one? All right, so I would like you to try this exploration. So take a calculator, compute the following, and then see what?
Into the regular calculator or graph?
The regular calculator thing, yeah. Okay, so log of 4 times 10, log of 4 times 10 to the 2nd, log of 4 times 10 to the 3rd, and so on, all the way up to log of 4 times 10 to the 10. Tell me what pattern in the integer parts of these numbers you notice. What about the decimal parts? And then how many orders of magnitude greater is 4 times 10 to the 10 than 4 times 10 to the 1? Okay. Go for it. You can just write it down off to the right there.
Wait, we answer the thing.
Yeah, just off to the right. See where it says 1, 2, 3. You can just answer the question. Well, number 1 obviously won't have an answer, but number 2, 3, and 4. Okay, is that enough time?
Yeah.
Jillian's breaking the school policy, so I'm assuming that's enough time.
What?
Huh?
I only heard the first part.
I said Jillian's breaking the school policy, so I assume you've had enough time. Okay. All right, so you should have gotten something like this. And so that first question, which is, what is the pattern of the integer part? It goes up by 1, right? So up by 1. Then number 3 said, what is the pattern of the decimal parts? That doesn't change, right? So that it remains unchanged. So let's write unchanged. And then 4, how many orders of magnitude greater is 4 times 10 to the 10th than 4 times 10 to the 1? 9. Okay, and so you can see what we mean by logarithms being able to help with large numbers. So you went from 10 to the 1, or the log of 4 times 10 to the 1, compared to 4 times, or the log of 4 times 10 to the 9, or 10th, which is a huge number, but the logarithm only went up by 9, right? If you go up here, you see that it went from 1.6, and I didn't do it all the way out here, but log of 4 times 10 raised to the 10, it went up by 9, okay? So what logarithms can do is they can take these really massive numbers. There's a huge gap between 4 times 10 to the 1 and 4 times 10 to the 10, right? Like 9 orders of magnitude gap. Okay, and it can condense it down to a scale that only goes from, 1 to 9 or 1 to 10. Okay, so that's the power of logarithms. And then, so actually, what I want to do is, if you flip your page over on the back here, a really useful scale that's logarithmic is the decibel scale. Okay, for audio, audio levels, right? Sound levels, okay? And so it's a logarithmic scale. So look at the intensity here, okay? So the threshold of hearing is at 0 decibels, okay? And here's the intensity in some unit that I don't know about or that I don't understand, but it doesn't really matter. So then it goes up by a factor of 10, and we're here at 10 decibels, so that's rustling leaves. Then it goes up by a factor of 10 again, and you can see actually, this is nice. This is even better over here, right? The number of times greater than the threshold of hearing. So here it's 10 to the 2nd power. So a whisper is 100 times louder than the threshold for hearing. Okay, then we go up to normal conversation. That's 10 to the 6th, right? That number of times greater than the threshold of hearing. And so as you go up every 10 decibels, you're going up another order of magnitude. So we go up from vacuum cleaner to, the difference between busy street traffic and vacuum cleaners, 10 decibels. It's another order of magnitude larger than the previous one. And it keeps kind of going like this. And so when you go from, so you're like, 100, there's not that much of a difference between 100 and 110. It's like, no, there's actually a lot, right? There's an order of magnitude difference. It's 10 times louder than the Walkman at maximum level. Well, Walkman. This is an old chart. But anyway, you get the idea here. Okay. So any questions on that chart there?
Does it sound for pain?
What?
Does it sound for pain?
Where it starts to hurt your ears, yeah. Mm-hmm.
Oh,
Yeah.
I was
Yeah. Yeah.
Oh.
Yeah.
I didn't know pain made noise.
No, yeah.
Sure.
No. It's just when it starts to hurt your ears, yeah.
That makes sense.
Yeah, and then you can see here at 160 decibels, your eardrum is toast. So, okay, cool. Any other questions on the decibel scale thing?
How much negative and how much not negative?
So we're a little bit beyond like my understanding of sound here. I don't understand what these units are, and so they, like 1 over 10 to the negative 5th is 1 over what would it be, 10,000? 1 divided by 10,000. And, if you multiply that by 10 and then by 10 again, eventually you've got 1 over 100 and then 1 over 10, and then it's 1 over 10 times 10, which is just, 10. And then, you just keep going. So, eventually you get to... What's that? Yeah, kind of. Yeah. All right, so let's go back to our... Actually, do I want to answer those questions while we're talking about sound? Yeah, I guess. No, I don't. Never mind. I lied. Okay. All right. Back to the front. So there are other applications of this. It's not just sound. Another common use of a logarithmic scale is the Richter scale. Okay, so here's the formula for the magnitude of an earthquake. So R is the magnitude of an earthquake. A is the amplitude in micrometers of the vertical ground motion. So that's A. A is the amplitude of how much the ground has moved vertically. T is the period associated with the wave in seconds. So that's how long it takes to cycle, one cycle of the wave. And then B accounts for the weakening of the wave with increasing distance from the epicenter. Honestly, we don't care a lot about this. What we're going to be looking at is comparing magnitudes. Okay? And so this is what we're going to be looking at when we compare magnitudes. So like we want to compare the magnitude of one earthquake compared to another earthquake. You guys need to get some more sleep. My goodness. Sorry. Well, sorry. Anyway, so when we're comparing magnitudes, what we care about is the ratio of the amplitudes. Let me show you what I mean. Let's look at an actual example here. By the way, R means Richter scale value. So R1 and R2 is the Richter scale value. So let's look at an example that'd be easier to kind of understand. I don't think so. I think all you have to do in the assignment is look at like comparing different earthquakes. So yeah. Okay. So how many more times? Oh, that's a typo. How many times more severe was the 2001 earthquake in India, which had a Richter scale level of 7.9 or value of 7.9, and the 1999 earthquake in Greece, which had a Richter scale value of 5.9? Okay, so that's what we want to compare. And again, this is the formula that we're using. So the log of A1 to A2 is equal to 7.9 minus 5.9. So we're just putting in R1 and R2 and then comparing them. Again, what we care about is the ratio of these two values. Okay. Does the A go through the amplitude? Yeah. Yeah. Okay. So this is 2, but it's going to turn out not to matter, and I'll show you why here in a second. So we have the log of A1 over A2. And again, we don't care what A1 and A2 are. We care about what their ratio is. Okay. So if I want to solve this for the ratio, or in other words, just what A1 over A2 is, I'm going to raise both sides with a base 10, or exponentiate both sides with a base 10, just like we did yesterday. And I get this as my ratio. A sub 1 over A sub 2 is equal to 100. Okay, so how many more times severe was the India earthquake compared to the Greece or the Greek earthquake? 100 times, right? Yeah, it was 100 times. And so it was 100 times as severe. And you can see that it doesn't really matter what A1 and A2 are because we're looking for the comparison. The comparison is that they're, the difference between them, or the ratio between them, was 100. And so, what's that? It's like your X, yeah. Okay, so that's kind of it for the Richter scale. Questions on that? All right, let's talk about pH for a second. Okay, so here's the formula for pH. We saw this in the video, right? pH is equal to the negative log of the H+. H+ is the hydrogen ion concentration. Okay, so let's analyze some different stuff here. So some sour vinegar has a pH of 2.4. That'd be really acidic. Excuse me. And baking soda has a pH level of 8.4. We're going to use this formula to figure out the hydrogen ion concentrations of each one. Then we're going to figure out how many times greater is the hydrogen ion concentration of vinegar compared to baking soda. So then we'll do a comparison. And then how many orders of magnitude do those concentrations differ? Okay. So part 1, though, is just figure out what is the H+ concentration in each one. So we have pH of 2.4. 2.4 equals the negative log of H+, which we don't know for either of these. So I'm going to times both sides by -1. That'll give me a positive there and a negative here. So just do that without writing another line. And then I want to get h plus by itself. So what should I do to get h plus by itself here? No? Yeah, exponentiate with the base 10, right? 10 to the left, 10 to the right. So I get, on the right, just h plus. On the left, I get 10 to the negative 2.4. So it's just 10 to the negative 2.4. Let's leave it like that for now. In chemistry or something? Gotcha. Yeah, we could make up a formula. It wouldn't be that hard. Okay, so then we'll take 8.4, set that equal to negative log of h plus, times both sides by -1, and then exponentiate with the base 10. So I get 10 to the negative 8.4 is equal to, these cancel each other out, and the h plus. That one was for the baking soda. All right. Questions on getting the H plus or the hydrogen ion concentration? Okay, so part B says, how many times greater is the hydrogen ion concentration of vinegar than baking soda? Okay, so how many times greater? What? Hold on. Okay. Okay, so again, what we're comparing these, we want to use a ratio. So the ratio of both hydrogen ion concentrations, we want to compare the ratio, or not compare the ratio, but we want to look at the ratio. So 10 to the negative 2.4 divided by 10 to the negative 8.4. If we simplify this, what do we get? We're going to have to use the exponent properties, right? So I'm going to take negative 2.4 minus a negative 8.4. So that's negative 2.4 plus 8.4. So that's 6. Oh, just 6, right? Negative 2.4 minus a negative 8.4. So I think it's just 6. So I get 10 to the 6. And that is 1 million, right? So the concentration of the hydrogen ion is 1 million times greater. Questions there? All right, how many orders of magnitude is that then? 6. Six orders of magnitude. All right, that's it. Oh, no, it's not it. What about the back? Okay, questions on this one? Sorry, you guys are practicing with phones. That's just going to be fine. Okay, how many orders of magnitude does a sound of 20 decibels differ from one of 90 decibels? 7, right? Yeah, 7 orders of magnitude. So you can just look at that in that way, or if you wanted to go, like to really follow the proper method, you take the ratio of each one. So you could kind of go over here at 20 decibels, you see that it's a 10 to the second power. And then at, what was the other one we're comparing? 90 decibels, it is 10 to the, 10 to the 9. Okay, so you take 10 to the 9 over 10 to the second. You get 10 to the 7th, and so yeah, that'd be 7 orders of magnitude. It doesn't have to be round numbers either. If you wanted to compare 25 and 92, you would just take 10 to the 9.2. Compare that to 10 to the 2.5. you get 10 to the 6.7, and that 6.7. 10 to the 6.7, we don't need this point right here. We need it to be pointless. And so, yeah, that'd be 6.7 orders of magnitude.
Anything else?
I don't think so. Do you want anything else?
No.
Okay.